All right, welcome back. We are going to go through another example of how to identify the points of inflections, find the points of inflections, and find the intervals where our functions concave up and concave down. And here's our function, x³ minus 12x minus 5. Here's a graph of this function f of x. And what we want to do is we want to identify where these points of inflection are. Now, if you recall, this is how you would justify your answer. So whenever you're doing this, I like to think, okay, we're trying to find points of inflection. So we got to figure out what we're looking for. So I'm going to justify our answer. This is what you have to do on AP tests and things. So we have some teachers that have to do that. I know my students have to do this. But what we want to do is, first for points of inflection. So when we think about this, I'm going to go through the process of how to identify this. So what we're looking for is when f, all right, f has a point of inflection. All right, point of inflection, all right, at x equaling blah, all right, so we're going to fill that in a little bit, all right, because what we have is that we're looking for when f double prime changes signs. So that's what we're looking for, when f double prime changes signs. Or when f prime changes from increasing to decreasing, or vice versa. All right, so on and so forth. So we're looking for either of those two things. Now, to figure this out, we have to figure out whether there's a change in concavity. Well, how do we do that? Well, change in concavity, when f double prime changes signs, well, we're probably going to try to figure out whether it's concave up and concave down then. So this kind of leads us to the next thing. Well, we got to figure out when f, all right, is concave up. That's going to be here, all right, because essentially it's when f double prime is positive. All right, when f double prime is positive. Or, as we know, if f double prime is positive, that means f prime is increasing. That's when it's increasing. In the same way, or a similar way, I should say, f is concave down, blah, all right, because what we're looking for is when f double prime is negative. Or when f prime is decreasing. Well, how do we determine this stuff? Well, one thing we can do is looking at a graph, okay, f. We know also that we have concave down is when there was a frown. So somewhere over here, we realize that it graphs like this, and then, oops, that's concave up, I'm sorry, I apologize. All right, there's a frown, and here's a more of a frown, oh, I'm so sad. All right, right there, and then there's a change. That change is the point of inflection. So our point of inflection appears to be right here, point of inflection, POI. And then it changes here, and you can see that we have point of inflection, then it changes the concave up like there. So this is concave down, where's a frown, that's what it looks like on an F, and then concave up, you can see that's where it's going to be happy, because you're happy up. All right, now, to do this, we're going to do now our analysis. Okay, this is the calculus involved, and we'll fill in all our stuff and verify what we have. So it appears we only have one point of inflection, because there appears to be only one sign change. All right, from concave up, or when f double prime only has one sign change. So let's figure this out. To do this, the easiest way, if possible, is just to look at f double prime. So f double prime, we're going to find this out. So what we got is 3x squared. We're not finding that first. We're finding f prime first to get the f double prime, which is going to be 3x squared minus 12. To find f double prime, we're going to have 6x, and then we're going to set that equal to 0 because we have to figure out the critical points of f double prime. What we have right here is we realize that it's going to equal 0. So looking at my graph, I'm pretty awesome because it looks like it's going to be at the 0. And now we're just going to verify that by doing a sign chart. Plug in our 0 here. We're going to go from negative infinity to 0. We go from 0 to infinity. And we're going to test out f double prime. F double prime, we're going to plug into our second derivative. So plug in a value anywhere on this interval. So like if we plugged in f double prime at -1, we're going to figure out is it going to be positive or negative. So plug that in, it's going to be negative, less than 0, negative. So that means that f itself, well, f prime is going to be decreasing. F is going to be concave down. In the same manner, we're going to go over to 0 to infinity. We're going to plug in a value on that interval. You're going to be like 1. Plug that into f double prime. We get a positive value. So that means f prime is going to be increasing on this interval. All right? And that means f is going to be concave up. We're looking at our graph. We can verify that that is true. From 0 to infinity, concave up. From negative infinity to 0, concave down. And yes, we have our 1 point of inflection at 0. So when x equals 0, all right, y is going to equal, plug that into our function, 0 is going to be negative 5. All right, so that's our point of inflection. We know it's going to be concave up from 0 to infinity, because that's when f double prime was positive, we identified. And we have concave down, all right, from negative infinity to 0, because that's when we identified when f double prime was negative. Well, that was kind of an easy one. All right, so hopefully this helps you out. Once again, to help you identify points of inflection, intervals where a function is concave up, concave down. Once again, I showed you to always think about justifying your answer. You always want to think about why. How do you understand this problem? How do we figure this out? Looked on the graph and then did our analysis to determine where those would be. So I hope this gives you some good insight on how to do some other problems. I'll have another tutorial or another example in just a little bit.